complexes. So we did a few things in octahedral complexes. We'll discuss the rest of them today. Okay, Josefa. Okay, so we were looking at octahedral complexes, and now we are looking at two different types of isomers, right? We look at geometrical isomers, and we look at optical isomers, that is enantiomeric pairs. For geometrical isomers, we interchange the ligands, and then we see if we are having the same configuration or different configuration, and we interchange the ligand. And how do we check if the ligands are the same ligands are at 180 degrees for two structure, then they are same. For optical isomer, we see whether a complex is having a plane of symmetry or center of symmetry. If it does not have plane of symmetry, it does not have center of symmetry, then it is going to have an enantiomeric pair. Okay, it is going to have an enantiomeric pair. Okay, so first of all, let's look at this remaining portions, MA3BCD. Some of you people were not present on Friday, so I'm telling you guys what we are doing right now. For example, if I have M, and in octahedral complexes, I have like this A3BCD, A, B, C, and D. Now, please listen very carefully. In this particular structure, you just have to look at the ligands which are 180 to each other. So if I have 1, 2, 3, 4, 5, and 6, so tell me this ligand A is 180 degree to what? Tell me.
A4.
Ligand A.
B4.
B4, right? Correct. So it is 182 to B. Then what about this A, the second A? It is 180 degree to
5C.
C. And this ligand A is 180 degree to
60.
Correct. This is D. Okay. Now we can make another structure in which we have. We can make a structure in which we have which A is trans to A. Okay, when we have 180 degree between the ligands, that is transposition. So AA, then you can have AB, then you can have CD, right? So this will be a completely different configuration, and this is another geometrical isomer. So I'm not going to make all the structures like this, but we are going to identify the number of geometrical isomers using this part. Okay, what is trans to what? First of all, how to do this? First of all, please see. In when you are going to have M A3BCD, in that case, first structure that you can make is all cis. That is, no same ligands are present at 180 degree. That means you'll have AB, AC, and AD. Then you can have A trans. In A trans, you will have AA, AB, and CD. Now there can be another A trans in which you have AA, but you are having AC and you are having BD. You can have another A trans in which you are going to have A, AA, AD, and BC. So you're going to get 4 different structures in geometrical isomers. And in these 4 different structures, this all cis is going to be a optically active isomer because it does not have any plane of symmetry or center of symmetry. Okay? Center of symmetry तो आपके पास नहीं होगा. As soon as you move from A6, you don't have any center of symmetry. But a plane of symmetry exists in the rest of the structures, but here it does not exist in this structure. It exists here also, and here also, but it does not exist in this particular all cis structure. So here you have an enantiomeric pair which is equal to 1. Number of optical isomers will be equal to 2. Now, these 2 optical isomers which we are having, one of it is already present in geometrical isomer. So total number of stereoisomers will be equal to 5 only. Okay, so 4, and this 4 includes one of the optical isomers, and the other optical isomer that is the mirror image of this all cis complex. So the total number of stereoisomers is going to be 5 and not 6. Please remember that. है ना? यहाँ पे जो आपके पास ये जो 2 optical isomers हैं, उनमें से एक already exist कर रहा है geometrical isomers में. So you have only 5 stereoisomers. But if someone asks how many GI is there, you will say 4. How many optical isomers are there? You will say 2. But stereoisomers will be equal to how much? 5. Why? Because in this 4, we already have this one optical isomer. Right? The next case. Ma2B2C2. Now, when we have Ma2B2C2, first of all, we can make all trans. All trans means A is also trans, B is also trans to B, C is also trans to C. Then we can make let us suppose have AA trans. So you have AA, but you have BC, and then the other is also BC. Then you can have BB trans. If we have BB trans, what will be the remaining? Tell me. We have only BB trans. What will be the remaining part? Guys. ऐसे नहीं चलेगा ना, दिमाग लगाइए आप लोग भी, ठीक है?
So
Tell me
AC.
what. Yeah. What about others? समायरा, मैमूना, हुजैफा, फहद, आप लोग को आ रहा है समझ में, नहीं आ रहा समझ में?
Yes.
So please tell me what are the remaining trans ligand. Mamuna, tell me. What will be the next one? Mamuna. Yes, Mamuna, can you please speak up?
So can you repeat?
आगे क्या होगा इसमें? What will be the structure of this geometrical isomer?
BC.
BC कैसे होगा? How many B's do you have? We are taking the structure, okay? Keep your mic on, Mamuna.
Yes.
How many B do we have?
2.
दोनों use हो गए या फिर बचा हुआ कोई भी?
It's used.
So what is remaining?
C. So CC.
नहीं, यहाँ पे हम लोग सिर्फ BB trans देख रहे हैं. Only B can be in trans. You understand what I say? You understand when I say trans?
Yes.
Tell me. क्या remaining हुआ?
AC.
And then?
AC.
Okay. Josefa, you will tell me if I have CC trans. So CC will be in trans. What will be the remaining 2 pairs? What will be the remaining 2 pairs? Okay, I have answered here. Josefa. Josefa, please. Okay. Ahmad. Okay, correct. Josefa, that is not right now. C is already used. आप लोग प्लीज इतना तो ध्यान रखिए, दो C है, दोनों यूज हो चुका है, राइट? कहां से आप दोबारा फिर से CC कर रहे हैं? Yes, correct. AB and AB. Yeah, that is right. AB and AB is remaining. Now there can be one more case. Just a second. Sorry. So here we have all trans, AA trans, BB trans, and CC trans. Then we can have a structure in which all cis is there. All cis का मतलब क्या हुआ? ना A के साथ A रहेगा, ना B के साथ B रहेगा, ना C के साथ C रहेगा. So what we are going to have? We can have in all cis AB, BC,
C.
okay. So how many geometrical isomers do we have? We have 5 geometrical isomers. One of it will be having this all cis one will be having the all cis one will be having an enantiomeric pair. So 2 optical isomers, and total we are going to have 5 plus 1, 6 stereoisomers.
So how can we use this?
They will ask you, no? They will give you a complex and then they will tell you how many geometrical isomers are there. So you identify what type is there. For example, you have okay, so in this case, they will ask you how many geometrical isomers are there, how many optical isomers are there. So what category is this? This is M, A2, B2, C2, right?
Yes.
So you just need to revise this table before going to the examination. Now, they're not going to ask you how we are going to get this many geometrical isomers, but it's better if you have an idea. अगर आप लोग ये table भूल जाएं, तो फिर आप लोग ये trans वाला method use करके खुद भी याद रख सकते हैं. Okay. So
Sure.
after we have M, A2, B2, and CD. So what we can have, first of all, let us have AA trans and BB trans. Then you will have CD. The next one that we can take is only AA is trans. In this case, we'll have BC and we will have BD. Then we can take BB trans. In BB trans, we are going to have what? AC and AD, right?
Yes.
What else we can have? Let us have CD trans. Let's take one all cis. So you'll have AB, AB, and CD, right? What else we can have? What else we can have? Tell me. Let us have AC, AB, and BD. Is this done? No, no. See? This is also new, right?
Yes.
We don't have anything similar to this, right? AC, we have where we have AC, we have AC only here, and it is not similar. So we can have one more, that is AD. And when we have AD, and we can have AB and BC. Is this done already? Where do we have AD? AD. Here we have AD. It is not done, right?
No, sir.
Okay. So this is another one that we can get. See if you can get anything else. You won't get anything else if you try also. Okay. So for this,
Yes.
you are going to get 6, and out of the 6, there will be 2 of them will be having enantiomeric pairs. Total optical isomers will be 4. Stereoisomers will be 6 plus 2, 8. Yeah. Then we have M, A2, B, C, D, E. For M, A2, B, C, D, E, you are going to get total of 9 geometrical isomers. You can do the complete thing. AA trans B, then you can get AB, then you can get AC, then you can get AD, then you can get AE. Okay, now this does start कीजिएगा. You have AA trans, you can have AB trans, you can have AC trans, you can have AD trans, you can have AE trans, right? So 3, 4, 5 parts यहीं पे होगा. Then you can have. After this, you will write down the rest of the structures, and if you can make anything else after that, also you will make that. Okay, so in total you are going to get 9 here. Out of this 9, you are going to have 6 enantiomeric pairs. Total number of optical isomers will be 12, but 9 plus 6 is equal to 15. This will be the total number of stereoisomers. For M, A, B, C, D, E, F, you're in total going to get 15 different geometrical isomers. All of them will have one enantiomeric pair. That will give you 30 optical isomers and 30 stereoisomers in total, because this geometrical isomer 15 is already included in optical isomers. Okay, that is why you're going to get 30 stereoisomers. Write this down. Complete the table. Raise your hand. Done everyone? Yes or no? Is everyone done?
Yes.
Anyone still writing? No. Okay. So please write when bidentate ligand is present. Okay. So first of all, we are going to look at tetrahedral complexes. And in your case, you are only going to learn about symmetrical bidentate. Okay. You're going to have only symmetrical bidentate ligand. We have complex, the number of geometrical isomers, the number of enantiomeric pairs, and the number of stereoisomers. Now we can have only 3 different categories. Since tetrahedral has a coordination number of 4, we can have M. This is my metal. Now AA is my bidentate ligand. Okay, A is my bidentate ligand. Metal is coordinating with A, and this also A twice. So this is my bidentate ligand. So another case that we can have is M, 1 bidentate ligand and 2 monodentate ligands. The other case will be 1 bidentate ligands and 2 different monodentate ligands. First cases, we have 2 bidentate ligands. So 2 bidentate ligands will give you 4 coordination number. Second case, we are having 1 bidentate ligands and 2 same monodentate ligands, that is going to give you 4 coordination number. Similarly, we have the last case in which we are having 1 bidentate and 2 monodentate, 2 different monodentate ligands. Now, since tetrahedral complex, agar aap logo ko yaad ho, in the last class I said, if there is any structure which is having only one bond angle. For example, in linear structure, we have 180 degree. In trigonal planar, we have only one bond angle, right? 120 degree. Similarly, in tetrahedral, we have all the angles are same, that is equal to 109.5 degrees. Now, when you have this type of complexes, this type of structures and geometries, in these cases, there will be 0 geometric isomers. Only and only if you have two different types of bond angles, then we are going to get geometrical isomers. For example, we have 90 degree here, and we have 180 degree here in square planar structure. Similarly, if you look at the octahedral structure, this also has like 180 degree, and there are 90 degrees here. So if you have more than one bond angle, okay, if all the bond angles are same, then it is not going to have any geometrical isomers. Okay, please remember that. So all of these will be what? 0, 0, 0. Is that clear? Yes or no, please tell me.
Yes.
About geometrical isomers. Okay. Now, next about enantiomeric pairs. So you know that we can either have plane of symmetry or center of symmetry. Now, tetrahedral complex, it is something like this. So it obviously does not have any center of symmetry, because if I go up in this case, then I will find a ligand. But if I go here, I'm not going to find a ligand. That means it does not have a center of symmetry. So we need to check only for plane of symmetry. Now, plane of symmetry, let us say we are taking a metal atom here. This is outside the plane, this is inside the plane, this is inside the plane, and we have, this is in the plane. The two straight lines is in the plane, and then we have outside some plane, and then we have a ligand that is inside the plane. So let us suppose you have ethylene diamine case. So you have NH2, CH2, CH2, NH2 like this. Okay. Now, here you can have anything X and Y. So I'm taking the very extreme case that both of these are different. Now, when I'm going to cut it like this, plane of symmetry is what? It is like a knife, you can cut it. So if you're cutting through a plane like this, and in this plane, what we are cutting the X, we are cutting the Y, we are cutting the metal atom. And this is going to pass through the bond like this. So please imagine that in the screen, we have X, we have Y, and we have the metal. Inside the screen, we have this part CH2, NH2. Then outside the screen, we have CH2, NH2. Okay. Now, inside the plane, what will be falling down inside the plane? You will be having CH2, NH2 that will be falling inside the plane. Similarly, outside the plane, you will be falling CH2, NH2. Now, since both of these are same things which are falling, we can say that it has a plane of symmetry. It has a plane of symmetry. Now, since tetrahedral complexes, it has a plane of symmetry, it will not have any enantiomeric pair. It will not be optically active. It will not be a chiral molecule because it has a plane of symmetry. Now, for the first case, MAA2, since if you have even one bidentate ligand, then you are going to get 0 enantiomeric pairs. So all of these are having, and also symmetrical bidentate, please remember, okay? In your case, it will be always symmetrical bidentate ligand. So please remember that. If you have a symmetrical bidentate ligand in a tetrahedral complex, you will not get any enantiomeric pairs because there will be a plane of symmetry passing through the plane, and you are going to get one part of symmetrical isomers outside the plane and one side inside the plane, and both of them will be same. Okay, so his total number of stereoisomers will be also equal to 0. So in tetrahedral complexes, you are not going to have any geometrical isomers, any enantiomeric pairs, any stereoisomers if you are having a symmetrical bidentate ligand. Now, look at the next case, that is square planar. Sorry, guys. Okay. So I was saying in square planar complexes, since the coordination number is 4, we are going to have the same 3 different types of complexes. In the first case, we have 2 bidentate ligands, making the coordination number 4. Then we have 1 bidentate ligand, that is coordination number 2, then 2, same monodentate ligand, now it is coordination number 4. Then we have a bidentate ligand. I don't know why this is happening, guys. Really sorry about this. Yeah. So when we have a square planar structure, in square planar structure, if we cut through this particular plane, all of these will be, all of this, we can cut in one singular plane. Okay, so please imagine if you have a phone or something like this, your phone has a molecular plane. If you cut in between the phone, okay, if you cut in between the phone, right? So square planar structure is like that only. You have the ligands in the 4 edges, sorry, in the 4 corners of your phone. And you can cut the ligands if you're passing a knife just between the phone like that. Okay, so there will be a molecular plane if I'm going to cut it like this. If I run my knife in this order. So since we have a plane of symmetry here, now if there is a plane of symmetry or a center of symmetry, there will be 0 enantiomeric pairs and it will not be optically active. So enantiomeric pair is 0 is in square planar case. No matter what is the case here, in all these square planar case, the enantiomeric pair will be equal to 0. Now let us look at the different complexes and try to interchange the ligand So first case is what? M, AA, and AA. Now in this case, as you can see here, if I am going to, we have same type of ligand. We have only one bidentate ligand. And we know that interchanging same type of ligand does not give any geometric isomers. So no matter what you do, you will always have A trans to A and A trans to A. That is not going to change in the first case. Those geometric isomers would be 0, so stereoisomers will also be 0. Now in the next case, we have metal. We have AA and we have AA like this. Okay. Now in this case also one more thing is that the bidentate ligand will always be cis to each other. It cannot be trans to each other. Okay. You cannot have a bidentate ligand which is trans to each other. It will be very far away. Trans. So that will be cis to each other. Here also you are going to get AA and AA. Now what you can interchange here, you cannot change anything. If you put the A here and you put this A here, then also you are going to get A trans to A and A trans to A. Now the last one here also, this is 0, 0. Now in the last one, you can make 2 structures like this. BN. But here also we have A trans to A trans to B. Here also we have A trans to B and A trans to A. So basically both of these structures are same. So this is not a change in orientation. This is not a change in orientation, rather it is a change in rotation. Okay, so we have rotated the molecule, nothing else. Here also we have A trans to A and A trans to B. Here also we have A trans to A and A trans to B. So here also it will be 0 and this will be also 0. Is that clear? Yes or no, please tell me.
Yes.
Okay. Now the last thing is octahedral complex. Right, the third case. Octahedral complex. We have complex geometrical isomers. enantiomeric pairs and stereoisomers. What are the different complexes we can have? We can have starting with MAA whole thrice. Then you remove, then you do MAA whole twice and A2. Then MAA whole twice. Then you can change both of these. So A and then dusra B. Then you can have M. Now this is, I mean, A2 case is completely done. Then you can start with MAA, only one bidentate ligand. And so remaining, how many ligands you can put? You can put 4 more ligands. So all of them are A, and A, first case. Then MAA, then you reduce this one, A3, and the other will be B. Then you can have MAA, you will have A2. Now this will be not BC, rather it will be first of all B2. Then you can have MAA, you'll have A2 and then BC. Now the cases of A2 is also over. Now you have to do the last case MAA, A, B, C, D. So this is all the cases for a bidentate ligand in the octahedral complexes. Okay. So these are all the cases. And this is also important, like you know what are all the cases and how, I mean, how I'm writing all the cases. Okay. So it is not something that you need to memorize it. It is completely logical. First of all, you have 3 bidentate ligand. If you remove one bidentate ligand, you are vacant. You are having 2 vacant ligands, right? You are having 2 vacant sites. So you can fill that 2 vacant site in 2 different ways. You can fill that 2 vacant site by either the same ligand or 2 different ligands. So यहाँ पे आपके पास देखिए, I filled the vacant sites by 2 same ligand, then 2 different ligand. Then I removed one more. Then I removed what? Then I removed one more bidentate ligand. Now when I remove one more bidentate ligand, we will be having 4 vacant sites. So you can fill the 4 vacant site by either all 4 same monodentate ligand, 3 same, 1 different, 2 same, 2 different. Then you can have 2 same and another different, and the last case will be all 4 are different. All 4 are different. Okay. So this is how you have to also picture this types of complex also. You don't need to memorize ki iska ye hota, iska ye hota, iska ye. Okay. Logically, you can conclude how many types of complexes can be made here. Now, the first case in geometrical isomer, you are going to have 0 because if you see this complex, you have A, and AA. Okay. Now, this is going to be AA trans, and AA trans. Now, this is not going to change even if you interchange anything in the middle. Okay. So that is not going to change interchange. So the orientation is not going to change even if you interchange the ligands because all of the ligands are same here. But let us look at the plane of symmetry and center of symmetry if there exists anything like that. AA. Now, if I look at the center of symmetry, please see if I go this side, what I am finding, tell me this is a bond between A and A, yes or no? If I'm going towards the left side, I'm finding a bond between A and A, yes or no? Please tell me. लिख लीजिए भाई, आप लोग टेबल लिख लीजिए, समझना नहीं है ना आप लोगों को. Write this down. Zero, 0, and 0. E3B will have naturally will be 0 and stereoisomers will be 2. This will have 3, 1, and this will be 4. 4, 6. This will have 6, and 12 stereoisomers. Okay. Checking. Write this down. Raise your hand once you're done. Raise your hand fast, guys. Adriel, Abdurrahman, Fahad, Huzaifa, Jiva, Maimuna, and Zaid. Waiting for you guys. Huzaifa and Maimuna waiting for you. Okay. Let me know if you're not done. And right next. Facial, that is FAC, and meridional. Meridional is MER. Isomerism. By the first point here, it exists only in complexes of M A3B3 type. M A3B3 type. Right, next point. In FAC isomer, the same ligands are on a common face of the octahedral complex. Of the octahedral complex. It next, in MER isomer, they are on a plane that bisects the octahedral complex. This is the definition that you're going to write in the examination, but when it comes to identify, you will be given some complexes and they will ask you what is the FAC isomer and what is the MER isomer for this complex. Okay, so in order to make FAC isomer and MER isomer, please don't rely on this particular definition. This definition is only if they are asking you what is a FAC isomer or what is a MER isomer. But if they are going to ask you to draw the FAC isomer and MER isomer, then if you have MA3B3, in this case, we'll have one FAC isomer and the other will be MER isomer. Now, in FAC isomer, we say a complex is in a FAC isomer when no two same ligands are at 180 degree. And we say MER isomer is when two same ligands are at 180 degree. So for FAC isomer, see this case M, you can have A, A, B, B, and B. Okay. Now, this is also, I mean, you cannot see it right now, but I will show you later on. This structure and this structure is same. Maybe you cannot see it right now, but both of these structures are same, and both of these are what? Same FAC isomer. For meridional, you just need to keep M. There will be 6 ligands. And you will have A bar kar dijiye. Then you write A anywhere else, then you write B and the rest of them. Okay. So as you can see here, we have 2A at 180 degree or 2B at 180 degree. That is why it is a mer isomer. Write this down. Let me know once you're done. Okay, guys, please see. In the first case, can I say that this is the first structure? This one? Yes or no? Can all of you see that?
Yes, sir.
This is the first structure, right? We have A. Let me erase this. Wait a second. Okay. Now, please see this structure very carefully. I'm not going to change the structure. I'm just going to rotate it, and you are going to get the second configuration. Okay, just look it here. Yes or no? Can all
Yes.
of you see that? Okay. So both of these are same structure. They are not different structure. Please yaad rakhiyega aap log. Okay. And as you can see, you can have all of these three in one plane like this. Okay. And all of these three are in one plane. ठीक है, ये तीनों एक triangle बना रहे हैं नीचे, ये ऊपर भी एक triangle बना रहा है. So in whenever you have a triangle, if you have 3 points, okay, अगर आपके पास 3 point कहीं पे भी हो ना space में, then always they are lying in one plane. Okay, please remember that. And this one plane is a face of octahedral complex. One face of octahedral complex. Okay. Please write this down. Okay, I hope you have written this, by the way. Now tell me this isomer, this cobalt. Tell me, is it a FAC isomer or mer isomer? Right. Send the answers in chat. Send the answers in chat. Fac or mer? It's facial or meridional? Send the answer, guys. Send the answer, guys. आप लोग सब लोग ना प्लीज ये देखिए कि कौन सा what condition it is satisfying. If there is any, if you have same ligands at 180 degree, it will be mer, and if you don't have any same ligand at 180 degree, that will be fac. It is not very complex. ठीक है ना, ध्यान देना बस आप लोगों को. I don't know why Abdul Rahman you have got it wrong. Okay, it's very basic thing. Do you see any ligand, any same ligands in 180 degree? Abdul Rahman, yes or no? Please tell me. Yes, Abdul Rahman. What is trans to NH3? NH3 के 180 डिग्री में क्या है? Yes, Abdul Rahman. It is NH3 only ना, तो क्या हो जाएगा? मर होगा. फैक्ट क्यों लिखा है आपने? देख के बताने का मतलब है आप देखिए कंडीशन सेटिस्फाई हो रहा है कि नहीं हो रहा है, उसको देखिए. ठीक है, बस ऐसे देख लेने से आपको पता नहीं चलेगा. यू हैव टू डू द वर्क हियर ना. आप एक किसी भी लिगेंड को चूज कीजिए, उसके 90 डिग्री में देखिए दैट डू यू हैव दिस और नॉट. आप दूसरा लिगेंड चेक कीजिए, उसके 90 डिग्री में देखिए क्या है. तीसरा लिगेंड चेक कीजिए, उसके 90 डिग्री में देखिए क्या है. सॉरी 180 डिग्री में देखिए क्या है. इफ यू गेट एनी टू सेम लिगेंड्स एट 180 डिग्री देन इट विल बी अ mer isomer. यू हैव टू चेक ऑल द लिगेंड्स लाइक दैट. ओके, और कहीं एक में भी आपको अगर मिल जाएगा तो वो मर हो जाएगा. एंड व्हाट आप लोग के लास्ट क्लास में हमने कहाँ तक पढ़ाया था? Okay, we are done with this chapter then, no? Okay, let us do some questions on isomerism. ये सवाल एक जो है ना आप लोग का, ये तो बिल्कुल रख लीजिए आप लोग. Wait, this one, not this one. This one. अच्छा, अब सबसे पहला सवाल है कि ये जो PT NH3 होल्ड NH3 होल्ड ट्वाइस एंड Cl2 होल्ड ट्वाइस है, दिस विल बी टेट्राहेड्रल या फिर स्क्वायर प्लेनर? Tetrahedral or square planar? What do you guys think? Send the answer in chat. ठीक है, इसको याद रख लीजिए आप लोग.
So this is of type MA2B2. Yeah.
Yeah, this is M A2B2. Okay, and please remember this is square planar. ठीक है? I know that आप लोगों ने आंसर किया है on the basis of ligand, right? यहाँ पे NH3 is what? It is strong ligand and Cl2 is weak ligand. अब दोनों के दोनों लेकिन सेम है. You have same number of NH3 and same number of Cl2. अब क्या देखें? Then we look at this particular metal atom. Now we know that platinum, we have nickel, then we have Pd, and then we have platinum. The lower series में आपके पास जो भी metals होता है ना, generally if you have same number of ligands, it is going to give you high del O. And that is why pairing happens and you are going to get square planar structure in this case. लेकिन वही है कि आप लोगों को del O की dependence on metals charge और rather on what series we are having, वो आप लोगों को नहीं पढ़ना है, ठीक है ना? तो आप इस केस को बस याद रख दीजिएगा. Pt NH3 whole twice and Cl2, it is a square planar structure. Okay. Remember this case, Pt NH3 whole twice and Cl2, it is a square planar structure. Now this is the case of what? M A2B2. ठीक है, तो इसके ज्योमेट्रिकल आइसोमर्स बनाने हैं आपको. तो सबसे पहले क्या कीजिएगा आप? AA ट्रांस AB ट्रांस उस तरह से समझिए, ठीक है ना? पहले आपको किस तरह से लिखिएगा? एक हम बता दे रहे हैं आपको, एक क्या होगा? All trans, in all trans you will have AA trans and AB trans. Sorry, AA trans and BB trans. एक ये बन जाएगा, ठीक है? दूसरा क्या बन सकता है उसके बारे में सोचिए.
AB
दूसरा क्या बन जाएगा आपके पास?
AB trans.
AB
AB.
and AB.
Yes.
Is there any other case remaining?
No.
नहीं ना, सिर्फ दो ही आपके पास केस है. We'll have M AA BB. This is trans, and then you are going to have M AB AB. This is cis. Okay, and this is cis platin. अगर NH3 वाले केस में बनाइएगा ना, PT NH3 chlorine and chlorine. So this is cis platin. और cis platin क्या होता है आपका? Cis platin is an anti-cancer drug. Okay, it is an anti-cancer drug. इस वजह से ये important है सवाल. दूसरा सवाल आपके पास जो था, इसको लिख लिया आप लोगों ने, जल्दी लिखिए. Done everyone? Yes or no? Please send me.
Yes.
Next लिखिए आप लोग. हाँ, ट्रांस भी बनाइए आप लोग, इसका ट्रांस भी बनाइए. You have to draw both the isomers. See, here you are having PTEN whole twice Cl2. Okay, now in this case, ये कौन सा कॉम्प्लेक्स है आपका? This is your कौन सा? What is the coordination number for this? Tell me. 6 होगा coordination number. 6 होगा. All of you agree with this? Yes or no? Samaira, Maimuna, Zain, Jiva, Huzaifa, Fahad. Tell me guys, coordination number कितना होगा इसका? 4 होगा या 6 होगा? Yes, Samaira.
So 6.
Why 6, Samaira?
So
Why
because
6?
ये
Here we have.
Bidentate, so 2 into 2 plus 2.
Yeah, that is true. Correct. ठीक है. So En is bidentate ligand, so the coordination number will be equal to 6. So the geometry is going to be octahedral. Now in octahedral, this is the case in which we are having M AA whole twice and A2. Is that right? Yes or no? Please tell me.
Yes.
यही हम आप लोगों को समझा रहे थे कि आप लोग पढ़ लीजिए जरा। यहाँ पे क्या था आपके पास? In this case, you can have how many geometrical isomers? You can only have 2 geometrical isomers. Those 2 geometrical isomers will be, please see. In one case, you are going to have AA in the trans, and in the other case, you are not going to have AA in trans. ठीक है? पहला केस क्या होगा? AA trans. A and A in trans. ठीक है? तो AA क्या है यहाँ पे? Cl and Cl है. So you'll put Cl in trans here and here, and then you are going to put NH3, NH2, 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 NH2 like this. ठीक है, दूसरा क्या बन जाएगा आपका? मेटल आपके पास प्लैटिनम है, अरे ये नहीं, Cl लिख दीजिएगा, and then you are going to have okay this. अच्छा, अब इन दोनों में आपके पास देखिए, if I cut it like this, this is going to be, this is completely trans and it is not going to have any enantiomeric pair. This one, however, it is going to have one enantiomeric pair. Please see. आप इसको ना इस तरह से भी ड्रॉ कर सकते हैं, like this, and you keep a mirror. ठीक है, यहाँ पे आपके पास क्या आ जाएगा? This one will be En. ठीक है, and then this one will be En. Here you will have Cl and here you will have Cl. Okay, so both of these are enantiomeric pairs. I mean, today I'm going to leave you guys earlier only. Okay, no problem. This chapter is done. I just want to discuss what is the next chapter that you want to study, and then we can end this class. XCF4. XCF4 तो सिलेबस में भी नहीं है, आपको क्या करना है? That C block is not there in your syllabus now.
Yeah.
So देख लीजिए यहाँ पे, तो अब P block क्यों पढ़ रहे हैं आप सिलेबस में जब नहीं है अभी? तो कम से कम बोर्ड्स के टाइम तो मत पढ़िए।
Okay.
XC में कितने वैलेंस ये होते हैं बताइए? XC has how many valence electrons? Tell me. Who's that?
So not sure. So that's
Sorry?
why I asked. So उसके बारे में श्योर नहीं था मैं, इसलिए पूछा।
नहीं, xenon में how many valence electrons are there? Tell me that ना. Xenon कौन से ग्रुप में आएगा?
F.
ग्रुप पूछ रहे हैं हम, ग्रुप।
Sorry.
1 2 3 4 5। अरे पीरियोडिक टेबल याद रहना चाहिए ना आप लोगों को। तो अब तो xenon is in the 18th group. Okay, it is a noble gas. Xenon is a noble gas. Okay, now
Yes.
it will have how many valence electron? 8 valence electron. अब 8 में से 4 are used for bonding. Can you see that? Because you have 4 fluorines. Yes or no?
Yes.
No. You have 4 bonds plus remaining how many electrons? 4 electrons. So those will be 4 lone pairs. 4 lone pair electrons, and you are going to have 2 pairs. Steric number will be equal to 6. 1 2 3 4 5 6. इस तरह से होंगे. You
Yes.
will keep 2 in the lone pair, and then the rest will be fluorines like this. Okay, so this is the structure of XEF4.
Okay.
ये बाकियों के लिए नहीं है, पता नहीं Z को P block पढ़ना है, पता नहीं क्यों. Okay, so this is only for Z. Chalo. Okay. Next, in the next class, we'll start aldehyde, ketones, and carboxylic acid. Yes or no? Tell me,
Yes.
guys. Okay, everyone.
Yes.
Okay. In the next class, we started aldehyde.